Okay guys, welcome to part 2 of lecture 8 on quantum interactive proofs, semidefinite programs, and multiplicative weights. This is for the winter 2020 offering of quantum complexity theory at Paderborn University. I have no announcements today other than this is the last lecture of 2020, so I wish you all a wonderful holiday break and try to dream pleasant dreams of this lecture as you hopefully enjoy your time off. Okay? Suppose I should have worn like a Santa hat or something today, but unfortunately I forgot that at home. So, we'll just have to have the most fun possible with the content itself, right? Rather than cheap gimmickry that goes on top. Okay, so last class, what did we do? Well, first of all, we defined this multiplicative weights method, right? Which was this very kind of age-old adage that, if something worked before, it's likely to work again. And in particular, it was an online algorithm that, given input from the environment in each round, it kind of updated its guess as to whose advice from a list of n advisors it should follow in each round. Then we also defined semidefinite programs, which, remember, are a very general notion of optimization problem, or a class of optimization problems, which in general we can solve in polynomial time in the dimension of the matrices involved. Okay, and we also defined this notion of quantum interactive proofs. And now in this lecture, we kind of put all those ingredients together. Okay, and where I'm going to start, to be clear, in the lecture notes, or we're going to start at section 2.3 of the notes. Okay, and so the last thing we did was we studied just semidefinite programs, or STPs for short. So the first thing I have to do today is finally write an arbitrary quantum interactive proof as an STP. Okay, that's going to be our starting point. And then what we'll do is we'll use the multiplicative weights method to solve the STP in polynomial space. And this will prove the containment QIP is in p-space, which is going to be the main result of this lecture. Okay, so let me just briefly remind you that in a quantum interactive proof, right, the setup we can have, remember, was we could always reduce it to 3 rounds. So there's going to be a verifier V, a prover P. Remember, the prover is unbounded, meaning arbitrary unitaries allowed, don't have to be polynomial time computable. And in the first round of the protocol, we're going to assume that the prover sends some message M1, okay? And remember that we can assume without loss generality that in QIP, what the verifier does after receiving the first message is they flip a random bit B. So this is just a random bit B, okay? And upon receiving that random bit, then the prover sends the second half of their state, in some sense, M2. Of course, they could also do some operation that depends on B after they've gotten M1. Sorry, after they've committed M1. Okay, so this is the basic protocol we're going to analyze, and let me just double check. But I believe we can assume without loss generality, right, that completeness is 1. And soundness is a half plus epsilon, kind of for any small epsilon that you like. So fix your favorite constant greater than 0. Okay, so this is the basic compression result for QAP we're going to assume in the background. Again, that's a non-trivial assumption. Classically, for classical IP, right, you can't do this compression to 3 rounds. It doesn't work, as far as we know. Okay. Good. All right, so now let me show you what the actual protocol is going to be in a little bit more detail, right? This is the high-level sketch, right? So to write it as an STP, I need to give you a little bit more details. So quantum interactive proofs as STPs. Okay. So this is the verifier, this is the protocol. Okay, so step 1 of the protocol. The prover, who's Merlin, sends the verifier. By the way, if I haven't stated explicitly in these lecture notes yet, I'm not a fan of the names Merlin and Arthur. They drive me a little crazy. So I try and use prover and verifier, but I might switch back and forth, right? I might forget that I'm supposed to hate Merlin and Arthur. Okay, prover sends the verifier some density operator. Okay, so sigma. So that's basically what's going to happen in this round, right? When I send the first message, it's going to be the state sigma, and sigma is in the register M1, right? So in register M1, right? So probably a better way of writing this here would have been to say that I send sigma in subscript M1, right? That probably would have been the best way to do it. And this is message 1, and that's why I have a subscript of M1, right? Okay, round 2. So the verifier, and you know what, from now on I'm not even going to write a prover and verifier, I'm just going to write P and V. Okay, so V, the verifier, has a pair of measurements. Okay, so what do they have? They have P0 and identity minus P0, that's one measurement. And they also have another one, P1, identity minus P1. Right, so this is just, again, for an arbitrary QIP protocol, right? In mind. Okay, so because basically they're going to flip this random bit B, and depending on which bit they get, you know, that's the measurement, either the P0 case or the P1 case that they're going to apply. Okay, so either this one or this one, depending on their random bit B. That's the idea, right? So in mind, let me be clear that, of course, these guys are all positive. Okay, and they're between 0 and identity. Acting on, so this is important, right? Where does the measurement act on, right? Where does V's measurement act on given this picture? Well, the main quantum the quantum registers here are going to be the message registers M1 and M2, right? So this measurement will act jointly on M1 and M2, of course. M1 tensor M2. Okay, there you go. So the verifier chooses B in just the set 0, 1, so it's single bit, uniformly at random, sends to the prover, okay? And what does the prover do? The prover sends the second message, M2, whoops, that should be in red, right, to the verifier. Okay, so all we've really formalized here, what we've added to this picture is that this random B basically, oh sorry, I still have to say the last step, right? The verifier measures, which one? Well, PB, so you'll note I'll write the B in red. So that's the connection between the random bit and the measurements on M1 tensor M2, and whoops, accepts if and only if the outcome is PB. Okay, that one. Okay. So that's the basic protocol, and yeah, the only thing we've added is that we've explained kind of what this bit B has to do with anything, right? And it's basically hiding a pair of measurements. Of course, now, let me be clear. Everybody, including the prover, knows what these measurements are, right? These are public available, but the prover just doesn't know which of the two measurements, P0 versus P1, is going to get applied, right? And so the point is that, you know, once I give the prover B, the bit B, of course, at that point it knows, okay, which of these two sets of measurements is going to get applied, right? But at that point, they've already committed the first message, right? They've already committed sigma, right? So, you know, there's this notion of kind of a commit, and then this bit B is revealed, this random bit B. Okay, and then once it knows B, and conditioned on the fact that it's already committed to this partial state sigma, basically, now P can send kind of some remaining message on M2, okay, to try and kind of clean up sigma as much as possible to make the verifier happy for whatever the random choice B was. Okay, that's the rough idea. So let me kind of, I've given you a pair of measurements that are going to, each of which is picked with probability 50%. Let me write them together as one joint POVM measurement for the verifier, instead of writing them separately like this, right? So the acceptance POVM for the verifier, right? What is it? Well, it's just, let me define it this way. Q Okay, so I'm going to use this over and over again, so that's important. So it's, so C, I suppose you can call it the check register if you like. I don't entirely remember what I was thinking when I wrote this in the notes, but that's presumably what I was thinking. So what's the idea, right? Basically, with probably 50%, I get 0. With probably 50%, I get 1. So, these are supposed to encode the bit B, if you will. And I've dropped the prefactor of a half here. It's going to go somewhere else. And, if I flip 0, then I'm going to measure basically P0, right? That's the whole idea. So what I'll do is I'll put P0 here. Okay, and of course, this is on M1 tensor M2, right? That's the space it acts on. And if I flipped 1 in the C register, right, in the random bit B, then I'm going to measure P1. Okay, so that's my operator Q. So this is the acceptance POVM, right? I don't want to say that, but okay, this is the acceptance POVM. Okay, so it encodes this idea that there's a bit flip B, right, and conditioned on what the value of B is, there's the measurement attached to it that corresponds to B. Okay. Okay, and so what is corresponding to, this is the POVM, the joint POVM, and now we can do something similar, right? We can write the state that the prover prepares, given B basically, in some nice joint way as well. Okay, so correspondingly, right, the prover prepares the joint state, the joint state rho B, right? So it receives B, right? And when it receives B, right, basically, essentially what it's doing is it's sending over its second half of the state, right? So the first half of the state, so this state acts on two registers, right? It acts on the part he's already committed, or she's already committed. And now, depending on B, there's something else that goes down on M2, right? So once you get B, then P can really finish preparing the state, if you will, on both registers. And of course, it will be dependent on B in general. Okay? And so that's what happens dependent on B. And now, of course, I can write this as a full mixed state, right? Because remember, I can denote things like random coin flips in terms of mixed states, right? So let's do that. Let's write the whole thing so we kind of get rid of the conditioning on B in some sense. So therefore, the density operator prepared by the prover is what? I'm going to give this a name as well. It's going to be called X throughout. And what is this really? It says, well, with probability half, right, I know I receive 0. Right, so that's, by the way, where the probability half went, right there. Instead of writing it here, I've written it here because I want this to be a density operator. Right, whereas Q does not need to be a density operator, right? It's a POVM. So X, with probability half, we got 0 in this, I guess, check qubit, the random qubit B, basically, right? And if I got 0, then what did I do? Then I prepared rho B, rho 0, sorry, more accurately, right? And with probability half, I got 1 in the C register. And if I got 1, then what did I prepare? Well, then I prepared rho 1. Okay? And again, for clarity, this is on M1, M2, and this is on M1, M2. Okay? So that's the POVM right here. This is the verifier's POVM. And once we write that this way, then we can think about the full density operator for the prover. Prover's density operator. Okay? And of course, what is the maximum probability with which the prover will cause the POVM to accept, or the verifier to accept, right? Which is what the goal is of the prover. Well, now, I've written it all in terms of one big operator on both sides for both POVM and density operators, so I just put them together with a trace now, right? So this is exercise 26. And basically, this says that to show that the probability that the verifier accepts now is what? Is equal to the trace of Q times X, right? So Q is, of course, coming from, well, okay, how do I do this without dissecting too much stuff? That's up there. And X was the density operator that is sent to the verifier. Okay, so that's just straightforward, right? That expression there. Okay, and now the nice thing is that these things are block diagonal, right? I mean, I have 0 tensor something plus 1 tensor something, right? So if I think of this as a matrix Q, right, I can write it as, this is the 0, 0 block, right? And this is the 1, 1 block, right? I could write it as P0 up here and P1 over here, and just 0 matrices everywhere else, right? And X also has this property. It's also block diagonal in this sense with respect to the C register. And therefore, we only need to kind of multiply out the diagonal terms. And I'll let you work this out on your own, but when you actually do this multiplication, what you'll get is a half times the trace of P0 times rho 0 plus the trace of P1 times rho 1. And think about that for a second. This is more or less what we expect should come out, right? Because it's probably a half, I chose the bit b equals 0 as verifier, and then the prover prepares rho 0, and I measure p0, right? So that's this term, and it'll probably have, we get subscripts 1 instead. Okay, so this is just how you formalize all that using these big funky looking operators on all the spaces. Okay, so that's the basic setup, and now we have to think about kind of constraints that are on this this setup, right? I mean, so in particular, right, what I said here is I cheated a little bit here, right? I mean, I didn't really cheat, but in the sense that here I said that, P prepares this joint state, right? The prover prepares this joint state rho B. But here we really have to be careful because he doesn't prepare this joint state in one shot, right? He prepares it in 2 shots, right? First, he commits half of it, and then conditioned on B, he prepares the second half, okay? So somehow we do need to capture that kind of commitment process. And the way we do it basically is, so here's the catch, right? What we know is that this is true, right? So you can imagine that what happens is that, sorry, let me just write out the full thing first. Okay, so this was the committed state in round 1. Okay, and what am I looking at here? Well, these two guys are acting on M1, M2, right? These are the full state prepared. Let's say rho 0 is what gets prepared when the secret bit is B0. Rho 0 is the joint state on M1 tensor M2 that gets fully prepared and sent over, right? And same thing for rho 1. But in both cases, right, only the part on M2 can depend on B, right? The part on M1, the first message, is independent of B, right? It's just a sigma. And so this condition captures the fact that if I throw away the second message, right, regardless of whether ultimately the prover prepared rho 0 or rho 1, what you see on the first register M1 is just sigma. Okay, there has to be this consistency constraint. This is the commitment. Okay, good. Now, one thing that's worth mentioning, and it's a very nice fact to always keep in mind, but is important because we have to make this, well, exercise 27, we need to understand kind of what freedom or what abilities basically the prover has under these constraints, right? And the basic idea is this. Let me write the fact down first, right? So consider any pair of purifications psi 0 on AB, psi 1 on AB of some density operator sigma B. Okay, so remember a purification just means that, I had some density operator which was possibly mixed on sigma B. And now I can think of 2 pure states, right, on A and B, psi 0 and psi 1, which if I were to trace out A on both of these states, right, I would always just reduce back to sigma B. Okay, that's what it meant to be a purification. So, okay, for clarity, right, that just means that trace out of A of psi0 should equal to sigma b. Okay, and same thing if I were to put a 1 here, it doesn't matter which one I choose. Okay, so this is the definition of purification. Okay, now the claim is that prove that there always exists a unitary. It doesn't matter which psi0, psi1 I chose, right? Prove that there exists a unitary U such that UA, tensor identity on B, of psi0 on AB equals to psi1 on AB. Okay? So this is actually quite an important statement. What it really says is that I can always move from any pair of between any pair of purifications for some shared state sigma b, right, by locally acting on the part that's not shared, right? Sigma UA in this case, right? UA acts on the register A, which is not the register which contains the joint sigma component, right? So in our picture, for example, let's apply this. What is this really saying in our picture, right? This is saying that you should think of this as message 1, and this is the message 2 space, right? So what it's saying is that once the prover has committed message 1, whatever that is, right? And maybe in the end they wanted to send one of two purifications of that, psi0 or psi1. But of course they don't know which one to send ahead of time, right? Because they don't know what B is. This basically says that it doesn't really matter as long as these two guys are both purifications of some joint state sigma B, or sigma on M2 in our case, right? Then they could always kind of switch to whichever purification on the joint space that they wanted to actually send, right? And they can do this just by acting on the part of the message that they still have in their possession, right? M2, right? Remember that M2 over here is still in the prover's possession at this point, right? So this is saying that once they learn B, they can do a unitary here, right? And that will allow them to kind of send effectively whichever of the two purifications of the first message that they actually wanted to send. Okay. So, I mean, this is just capturing the idea that dependent on B0, whatever the value of B is, right? The prover still has this degree of freedom in kind of modifying their message to kind of steer it towards a direction that will make the verifier as happy as possible, given the particular choice of B, right? That's what this is capturing. Okay. So these are the basic definitions we need, right? Let me remind you, because I'm going to write all this down again. Q is just the joint POVM that the verifier measures. X is going to be the density operator that represents what the prover prepares, right? And we have this constraint here that regardless of which joint state the prover sends, if you throw out the second message register, you should always get back your commitment on the first message register. Okay, good. So now let's write down the STPs. And I'm not going to go through the derivation of the dual. I'm just going to state it and use it. So the primal, I'll make some comments about this, of course, but the primal will make mostly sense. The dual is probably not obvious a priori, but it can be worked out. Okay, so I'll just refer to these as a P for primal and D for dual. Okay, and so what are we doing? Well, of course, we want to maximize the acceptance probability, right? So we maximize trace of Q times X, right? So remember, this is POVM. This is prover's density operator. I suppose this is why in the notes I decided to keep using Merlin and Arthur, because now I'm using P for primal. Okay, but I'll be stubborn and I'll keep using P for both primal and for prover, unless it really gets to me, in which case I'll switch to Arthur Merlin. But I'll try and make the context clear. Okay. So we're trying to maximize this overlap, of course. And what are the constraints, right? So subject to what constraints? Well, of course, the first state you commit should be a density operator. So sigma of M1 should be positive, right? It should also have trace 1. So that's the density operator. And the other thing I want, though, is this condition that if I trace out the second message register, right, I should get back the committed state, essentially, right? So if I trace back, if I trace out the second message register of x, right? X is the joint density operator that's prepared, right? What I should get is this thing, identity. Okay, so the point is that you're going to see this sigma show up again. Okay, so that's that consistency constraint we had up here, right? This one over here. Of course, this one didn't deal with the C register, which held the secret bit B, right? So that's why here, when you also take this into account, you should get an identity here. And here, of course, I'm using, where's this identity coming from? Well, I'm using the fact that if the prover is honest, right, in this STP, your x should look something like this, right? And if you trace out M1 of this, right, what you should really get is exactly identity tensor sigma, right? So it's basically what you would get if you trace out M1 out of this ideal proof x. Okay, so that's why I see this identity C here. Okay, and what does the dual look like? Well, the dual is going to have, oh, I guess it's a typo. Okay, so now we're going to minimize. Okay, and what are we going to minimize? Again, this might not be obvious at all where this comes from. So the dual variable now is y, and y is going to act on, well, I'll show you in a second, but on C and M1. And we want to minimize basically its largest eigenvalue. It's going to be positive, so this is going to be its largest eigenvalue. And subject to the constraints that y, which acts on C and M1 only, not on M2. Okay, this thing is larger than Q, right? Q is this bad boy over here. Right, there's Q. And last but not least, this thing is going to be positive. Okay. I suppose you don't really need this condition. Think about this. Why you don't really need to explicitly state this condition. Why? Well, look at this condition. Q itself is positive semidefinite, right? It's just going to be your, it's a POVM element, right? So if I'm saying that y tensor I is bigger than something positive, then certainly this thing is positive. And well, this joint thing can't be positive unless y itself is positive, right? Because tensoring with identity doesn't change your eigenvalues, it just creates many copies of them, right? So there's a sense in which you could just throw this out if you like, right? This is a redundant constraint. Okay. So these are the basic STPs. Let's just look at them for a second. So like I said, these two together just make sure that the committed state is a density operator. That's fine, right? And you'll notice here that there's nothing here, right? The way I've written this, right? There's nothing here that says, x should look any particular way, right? I mean, right now, x is just some arbitrary operator here, right? Oh, sorry, I missed one constraint here. I was wondering where this went. It should be positive, right? Because ultimately it will correspond to a density operator. Okay. But notice how I'm not saying anything about the structure of x. This could be any positive operator, whereas up here, let's have a look at x, right? X had this very, very specific form, right? It was block diagonal on the 0 and on the C register, right? 0 tensor row 0, 1 tensor row 1. But, I haven't enforced this in the STP in any sense, right? So let me just comment about this. So ideally, we want x to be block diagonal on C. Okay, so i.e. it should look something like, there should be some register, some state x1, some state x2 here, or some operator, and you should have zeros. Okay, and this is where you set the C register to the 0 and 1 block, right? So we want it to look like this, right? Or sorry, in my notes I used row. So let me be consistent with my notes, right? Right? Because these were the blocks, right? We sent these density operators row 1. Sorry, I should say row 0, right? Yeah, row 0. Row. Okay, you know what? At some point, it's just better to start over and do it right. So it reminds me of one of my favorite quotes I heard for programming, which is that there's never enough time to do it right, but there's always enough time to do it again, right? Try to take the time to do it right the first time. right? It'll save you a lot of time in the long run. So let's do it, right? Let's write row 0, row 1. Okay, so this is what we want x to look like, right? And we could, do this formally in the STP, right? I could have, instead of writing, x as this kind of big black box thing, I could have written it as row 0 and row 1 and then kind of stitched things together and still had an STP. But the point is that it doesn't really matter, right? Because Q here, remember Q is also block diagonal, okay? So recall that Q, let me get the definition back. Where was Q? Right? Q looked like this, right? It just put the measurement operators on the diagonal just like that, right? So this is what Q looks like. Q looks like P0, P1, right? And so the point is that without loss of generality, right, if I want to maximize the trace of Q times x for positive x, right, we can choose block diagonal x. Okay, so this is one of these neat tricks that you can always play, not always, but you can sometimes play with STPs, right? Which is that a lot of times you don't have to explicitly force certain structure on your feasible region. Instead, you can get it without loss of generality, right? And this is one example of that, right? And so this is just because. So this is exercise 24, basically. Sorry, not 24. Exercise 28. And the reason why this holds is that, the reason why is because if, let me write it this way, right? Suppose there exists, so if there exists an x, an arbitrary x, such that trace of qx equals to, whatever, let's pick some name y, right? Then there exists a block diagonal x prime, right, which is also positive, such that the trace of q x prime is equal to y. Okay, so this is how you formally state and try and prove these without loss of generality statements for STPs, right? You just need to prove that if there was some other solution that's arbitrary, I could always rework it to look exactly the way I want and get the same objective function value y. Okay, so you'll notice these are the same. And what's the basic thing, the basic property for this that exercise 28 asks you to prove is that prove that if A, B, B dagger C, so you have some arbitrary operator, which I'm writing in block format, if that's positive, then I can do something really, really simple to make it block diagonal, which is that I'll be as stupid as possible. I'll just throw out the off-diagonal blocks, and that will still be positive. Okay, so prove that this statement, this one here, is true, and then use that to argue this without loss generality claim. Okay. Good. So this means that I can assume without loss generality that the optimal solution to this STP will be block diagonal, just like I kind of wanted it to be in the ideal solution. Okay. And so another exercise, which we won't do formally here in the interest of time, but prove that, let me see, equation 1, I want to be consistent with my notes. Oh yeah, so prove that if we trace out M2, right, of x, well, okay, let me write out the full x the way we had written it originally, right? And remember that this is the one that acts on M1, M2, right? Same here, right? So prove that in our original kind of ideal version of x, what we're looking for, if I trace out M2, then I'll get exactly what we see in this STP, right? Which is this thing, right? Identity on C tensor sigma M1. So I want you to prove that to convince yourself of this fact. Identity on C tensor sigma, the committed state, on M1. Okay. Good. Okay, oh yeah, sorry. This is, of course, we're going to omit the factor half, right? Because we did, otherwise I don't think you get the right result. Yeah, because otherwise you'd get identity over 2, I believe, here. Okay, so to make that work out this way, we're dropping the factor half. Okay, but that's basically where this constraint comes from. The only funny thing is, right, you should have equality here, right? I'm claiming that if you gave me a solution of the right form, like 0 tensor row 0 and 1 tensor row 1, and you trace out the second message register, you should get back the first committed message. Here it is, right? This thing here, right? But I have this funny inequality, right? Why in the world? Okay. And again, this is just going to be like here, right, where I don't need to explicitly enforce structure on x to get it, right? I can instead just make x arbitrary, and we get kind of for free the fact that x without loss generality in an optimal solution can be taken to be block diagonal. Okay, and same thing here. This turns out to be without loss generality, right? And the whole idea is that if there was a solution basically that's strictly positive, right, so that this doesn't hold an equality, then there's another solution you can come up with which will make this hold an equality and will give you only a possibly better objective function. It will never be worse. So let me write that down. It's a bit of a mouthful. Exercise 31. Okay, so suppose that whatever solution for x you gave me, right, this was true, right? It certainly satisfied the constraint, so it's feasible, but it's not equal, right? So it doesn't hold with equality the way we would ideally like. Okay, so again, how do you prove that this is without loss generality? Well, what you should do in this exercise is give a new operator, give some x prime now, right, such that the equality does hold. So now I'm putting x prime in here. And now you'll notice the equality does hold, right? Identity on C tensor sigma m. So this is kind of the ideal behavior we want, right, up here. That's the ideal behavior. And the trace of, this is the objective function, right? If I plug in x prime, right, it can only be at least as big as the original operator x. Okay? This is the exercise, and again, these are all cute exercises. This is how you formally prove that you can assume certain structure in your STP without loss generality, without explicitly having to write it out. Okay? And the last thing I want to point out, which is currently a typo in the notes, and I do have to fix it, is So I made a big fuss last time about, in general for STPs, here we need a supermum and an infimum, right? But remember that when strong duality holds, right, then actually the primal will equal to the dual, and that dual will be achieved. Okay, so in other words, you don't need the supermum, for example, you can just put in a max. Okay, because there's no kind of infinite limit that goes somewhere that's never achieved, right, in the feasible region. And so the last point I want to make, and this is a nice exercise, exercise 32, is that prove that Slater's constraint qualification holds. Okay, and this of course immediately implies that strong duality holds. Okay, so just to refresh your memory, I know you were not dreaming about Slater for the last week. So what this says, remember, is that you want to come up with a solution to this STP so that all these inequality constraints are strict inequality. Okay, so for example, x has only strictly non-zero eigenvalues and positive, okay? And same for these things, okay? And that's Slater's condition, and once it's satisfied, we know that the best solution here equals to the best solution here, basically. Not in terms of the actual solution, but the solution value, of course, in the objective function. Of course, the variables themselves are different, right? Here I have a variable x, a primal variable. Here I have a different dual variable y. So you don't expect these to be the same. Okay. So the last thing we're going to do to make our lives a little bit easier is, and I'm not going to go through the details of this, but just like with the quantum Cook-Levin theorem, right? we wrote down our Hamiltonians, right? And it turned out to be easier to, instead of directly analyzing the Hamiltonians, we first did a change of basis with the unitary, right? And then, for example, the propagation Hamiltonian became very nice. It looked like this tridiagonal matrix that corresponded to a random walk. We're going to do something similar here. We're going to just kind of change variables a bit. And so the actual final STPs we'll work with will be the ones I write down now. They'll be quite similar. I'm just going to change one or two small things. Okay, and I'll write those in red. So here's the primal. Here's the dual. And now you'll notice a few things. So first, the trace. Before I had trace of x times q, right? X is the variable. And now q is missing, right? Where did that go? Well, keep watching and find out. So now I have this funny q phi of x, which was not there before. This is the same as before. I'll put these together because they're the density operator constraints. And this is the same as well. Okay, so now instead of having q in the objective function, now I have this mysterious phi, which I have to define shortly. I'll do that in a second. Let me just first write down the dual. Okay, subject to phi star. Sorry, this should be in red, of course. I think that should be the same as before. Wait, let me double check. What did that look like before? The dual. Yes. More or less the whole thing is new. Okay, so let me write the whole thing in red. Okay, M1, M2. Okay, so you'll notice, for example, this phi star is going to take y on C and M1, and it'll blow it up so that the resulting operator also acts on M2, right? That's why we can do this comparison. Okay, y, C1, M1, I think this is the same as before. All right, and so the last thing I have to tell you is what in the world is this technically it's called a superoperator. What is this superoperator phi, right? Well, it takes you from the register C, M1, tensor M2, right? And it's going to map you down into, well, where is it going to map you? Well, remember phi star, the adjoint map took you from CM1 to CM1, M2. So the reverse of that in some sense, the non-adjoint version should do the opposite, right? It should take you from C, M1, M2 down to C, tensor M1. Yes, okay. And so that's the signature for it, right? But what is the actual definition of the map? All it does is it takes in, give me an operator x, right? And it'll take x, and well, q, remember q disappeared up here, right? So what I'm doing is instead of thinking of it as q times x, by the way, let me be clear that if I had trace of qx, right, that's what the objective function used to be. Q is positive, right? So what I can always do is I could rewrite this as the square root of q x square root of q, right? I could break, q is positive semi-definite, so I could break it into its square root, just like you could for any non-negative number, right? I'll leave that as an exercise. And the trace means I can move the other half around, okay? And now this phi is kind of undoing that mapping in some sense, right? So phi is going to look like this. It's going to take q, x, but instead we're going to have minus a half, right? Because intuitively, I'm going to start thinking of x not as x, but x as this full thing implicitly. And so this phi is going to kind of strip off that q, right? Think of it that way. So again, it's just a change of variables, right? I'm changing basis. I'm kind of conjugating by q in some sense, or square root of q. Where did this thing go? Yeah, trace of M2. Nope. I knew something was fishy. This thing. Okay. And the adjoint map for clarity will look like this. Again, these things are not always trivial to work out. So what does that look like? Again, you have this q minus a half on both sides. And now you have the dual variable y. identity tensor M2. Remember, this acts on C and M1. Okay. So from now on, whenever I talk about primal and dual and I use P and D for that, I'm referring to these STPs henceforth in this lecture, okay? Good. So that's the setup. Now we can prove the main result, which is that QIP equals P-space. Okay, by the way, I know this is quite cryptic looking, so I certainly encourage you to stop the lecture here and just look at the course notes, look at your screen, stare at it for a little while, try to internalize as much as you can at this point, right? And then, you know, unlike in class where you can't just pause me and rewind me or fast forward me, you can hit play again and just continue when you're ready. Okay. So here is the main result. QIP equals P-space. Okay. So of course there are two directions to this. There's a trivial direction. Well, it's not really trivial in the sense that it's using existing results which are non-trivial. But what's trivial is that QIP, well, okay, let me go in the other direction. P-space is known to equal to IP, so this is non-trivial. Let me be clear. Okay, but this is trivially contained in QIP, right? That's the trivial part. And so, and this is an old result, right? So this is due to, for example, Shamir. Okay. So once you have this equality that P-space equals to IP, then trivially this means that QIP also contains P-space, okay? Because now you can also do quantum things, right? Roughly speaking. So the non-trivial direction for us, right, in the quantum setting is, well, how do you prove that QIP itself can also be solved or decided in P-space? Okay, so with a polynomial space Turing machine, right, it can take exponential time, but polynomial space, you want to, essentially, what's the goal, right? We want to solve this STP, right? You know, we've written down these STPs, right? And this STP captures the optimal acceptance probability for any 3-round interactive proof of the type we said, which was without loss generality. So as long as I can solve this semi-definite program in polynomial space, right, then QIP is in P-space, right? And of course, the problem here is that all these operators like X, for example, they act on order n qubits, which means the dimension's huge, right? I can't just write down this matrix in polynomial space, right? It's not obvious how you do that. So somehow you have to be clever. You have to solve this in some sort of succinct fashion. And you probably guessed that that's where multiplicative weights is going to come into play. Okay, but more on that in a second. Let me just say a bit of interpretation. Okay, so the first time you stare at this, you might say, you know, really? You know, that's it? Right? I mean, we add quantum to the picture, and we get absolutely no benefit over classical interactive proofs. Like, what? Right? What am I sitting in this course for, right? Like, what's the point, right? Well, here you have to be very careful. Okay, so let me give the interpretation in a few points. So the first point, of course, is that it's of course disappointing that QIP doesn't give you any power over IP, right? But another way to view this is that, you know, interactive proofs are so powerful that, you know, already they're powerful enough to capture even quantum things, right? I mean, so you can view this as a positive, right? That interactive proofs themselves are really, really powerful things, right? They're much more powerful than, say, NP, for example, right? So whereas we strongly believe NP is not equal to QMA, an interactive proof really is a jump above NP, right? Okay, so this is in the single prover setting, right? So there's one prover and one verifier. But you can go to the multi-prover setting, and there it's a totally, totally different story. So I'm going to undo your disappointment, if you will, and now I'm going to blow your minds, let's say, right? So in the multi-prover setting, it's actually known that classically, you know, the MIP, which is going to be multi-prover interactive proof. So now you have multiple provers, and they can't interact, they can't talk to each other once this protocol begins. Otherwise, they might as well be one prover, right? This is known to not equal to P-space, but to actually jump up to NEXP, okay? And you can think about a quantum analog of this, MIP star. Okay, and here you have basically two provers, and they share entanglement. So this is kind of like a Bell experiment, if you will. Bell inequality violation type experiment. And otherwise they're not allowed to talk, right? They can share this entangled state beforehand, and they can communicate with this verifier. But they cannot talk once the protocol starts. And what is the power of this? Well, if you were a pessimist, then you might believe that, oh, just like QIP equals to IP, maybe MIP star also equals next. And just this year, in fact, there was a breakthrough result which finally resolved the final complexity of this, right? So there was a sequence of works that kept giving better and better upper bounds on this, or lower bounds, I should say. And it turns out that this thing now we know is actually equal to RE. Okay, so these are the set of recursively enumerable languages. And in other words, this contains, among other things, the halting problem. Okay, now I'm going to do my best attempt at drawing a shocked face, right? So these multi-prover interactive proofs, if you have more than one prover, which we're not studying here, we only have one prover here. If you have multiple provers, right, then it turns out that you could verify even undecidable problems. It turns out to be extremely powerful, okay? Much more powerful than you could ever hope for in practice, right? So it just so happens that in the case of a single prover, you have this kind of funny phenomenon where things kind of briefly coincide, right? With NP and QMA, we believe they're different. Then for single prover interactive proofs, somehow they begin to coincide, classical and quantum. But then when we go to multi-prover, then that difference really just blows up completely. Okay. So that's what I want to say about interpretation. Now we can talk about the algorithm. How do we actually prove, how do we solve this STP in polynomial space, right? And the first thing I want to do is I want to give you the connection to P space, right? So that's, well, first let me say this is section 3.1. It's the actual algorithm we're going to do. Connection to P space. Here it is. Okay. So the naive idea here is what? We have an STP, right, that captures QIP, and that's this primal P. And so we can try and solve P using, example, something like the ellipsoid method. Whatever. I mean, we'd never do this in practice, but for a theoretical result, as long as you satisfy the mild preconditions of the ellipsoid method, this would give you, the dimension runtime. Okay, I'm obviously fudging a few of the factors, right? With last class, we wrote down the exact kind of the runtime of this ellipsoid method, right? But roughly speaking, it's going to run in time polynomial in the dimension, okay? And of course, that would immediately give you, if this worked, it would immediately tell you that QIP is in P space, ta-da, you're done. Except the problem, of course, is that for us, the dimension is exponential. Right, and this just goes back, let me scroll back up to P for a second, right? This is just because, these operators I have here, like X, right? These are, for example, sigma even. Let's look at this. Sigma was just a quantum state that the prover sent in the first round, right? That's some state on order n qubits, right? It's going to have exponential dimension, right? So I can't explicitly write down this STP, right? And to solve the STP, typically you have to write the thing down first, right? This is a classical thing. I mean, there are nowadays quantum algorithms for STPs, right? But the ellipsoid method is a classical method, right? It writes down the full thing. Okay. So we can't use this method, okay? And we need an alternate method. And in particular, we need some way to solve this STP in a clever way, okay? So let's ask ourselves, question, what can we do in P space? Okay. So here we're going to use a fact. It will be helpful to think in this view rather than thinking about a polynomial time Turing machine, a polynomial space Turing machine, right? I'm going to use the fact that P space equals a class called NC poly. And what is this, right? This is going to be, roughly speaking, the set of problems or languages decidable by uniformly generated. So, typically we like things to be uniformly generated in our circuit families. So circuits of, and now of course, they're not going to be polynomial size because otherwise you just get, well, P, right, classically. So we have to give up something, right? So they can be exponential size now, right? But what's the trade-off, right? I mean, if I have exponential size for general circuits, right, then I would get exp, right? So I need a catch, right? What's the restriction? Well, now I'm going to restrict the depth of the circuit, poly depth. Okay. So what that essentially means is that, my circuit C, right? Let me just kind of sketch this quickly. My circuit C, it's a bunch of gates, right? That means that this thing, the number of kind of input wires, this is exponential in the input size, let's say little n, right? So this thing really takes in a ton of gates, a ton of wires, right? But then, the number of kind of layers of the circuit, if you will, like this, the number of layers is going to be poly n. Okay, that's what we mean by the depth being restricted. Okay, and then maybe there's an output qubit and you're going to measure that, or classical bit and you're going to measure that. Okay, so this is roughly speaking NC poly. Okay, so this is the characterization of p-space we're going to think about. Okay, and roughly speaking, you should think of these as, okay, maybe I won't go there. I'll say a bit more in a second. Okay, but exercise 34, the first step of this, like why should we even be thinking about this weird alternate characterization of p-space, right? Well, exercise 34 says, convince yourself that Q can be written down. So Q, remember, is this, it's a constraint matrix, right, for, well, it used to be in the objective function until we did our change of variables, but it encodes this POVM, right? So it's a giant matrix, right? We can actually write down the full matrix, can be written down fully, okay? And so classically, with a circuit of size exponent and depth poly n. Okay, so this is kind of the starting point. Okay, so by the way, I didn't want to say NC poly here, right? Even though these parameters match on the left and the right, because technically on the left I'm producing a matrix as output, right? Whereas on the right, NC poly is solving decision problems, so the output's supposed to be 0, 1. Okay, but it's the same class of circuits. And so, why is this true? Well, this isn't very, you have to kind of look at the definition of Q, right? Why can I do it this way? Well, what was Q, right? Q, I'm going to go back to the definition all the way at the top, which at some point will come back to us. There you are. So this was Q, right? What was Q? It was just essentially this P0, P1, right? And what was P0? These are POVM elements, right? This is basically what you get, well, what the verifier gets by running a polynomial-sized quantum circuit in terms of a sequence of 1 and 2 qubit gates, right? And then applying some measurement, right? So if I were to explicitly write this out, right, of course this would be an exponentially large matrix, but, right, I can compute it efficiently, right? Whatever the gates were in the underlying verifier, these are 1 and 2 qubit gates. Each of those I could certainly write down, right, as an explicit exponential size matrix, and which I'm allowed to do in NC poly, and then I multiply those together, right, to get P0. But what is the depth of the circuit? Well, it's literally the number of gates I have to multiply out plus the measurement at the end, right? And I only have poly many gates. So the depth of the circuit is polynomial. Okay, so the reason why this works essentially, and again, if you didn't follow that, that's of course completely fine. I encourage you to stop the video and really think about it. This crucially uses the fact that Q, well, let me say the verifier. Verifier is a poly size quantum verifier, let's say. Okay, or quantum circuit, essentially. Okay, so that's kind of where the story starts. So in NC Poly, in that kind of class of circuits, right, I can always come up with a circuit which explicitly computes this full matrix Q. I can do that. Okay. So that's the first thing. So this is ingredient number 1. Okay, and how about ingredient number 2? Okay, well, that's a good starting point because now I can at least express, remember before we said these matrices like Q are too big. I cannot write them down in Poly space. So the naive ideas for doing this in P space won't work. But now there's an implicit way of doing it, right? I can do it in NC Poly, and I could give it, via this circuit, basically, right? By classically multiplying out the gates in the circuit. Of course, I'm not actually going to do the multiplication because then the matrix I get, I can't store that entire thing in memory at any point in time, right? I only have Poly space ultimately. Is that true? Yeah, well, I mean, I only have Poly space, right? Okay. So, okay, so the next thing is that it turns out that in these NC type classes, right? So before I said the depth was Poly, right? But usually if you see NC, the idea is that it's supposed to be a restriction of P, right? So then the size of the circuit would be P, and the depth will only be log now, right? So you kind of blow everything down or squish everything down by an exponential. But basically the premise here is that a lot of matrix arithmetic can be done in this very succinct fashion in NC, right? You don't necessarily have to have a full Poly size, a Poly depth. Like if I give you dimension D, I don't need to work in depth Poly D to do matrix arithmetic, it turns out. Many operations I can actually do with just log depth, okay? So in other words, another way of looking at this, which we won't explore here, is that you can parallelize, essentially, these operators, right? So NC can be thought of as the problems in P, let's say, which can be efficiently parallelized. Okay, so go have fun, look it up on Wikipedia or wherever if you want to learn more, but we're not going to take this viewpoint in this lecture because we don't need it, okay? So the whole idea here is that given D by D, whatever D is, right, matrix M, right, can compute many matrix operations via uniform circuits of what? Well, size polynomial in the dimension, right? And so for us, remember, our dimension was exponential, and that's why the size you get here will be exponential as well, right? But in general, maybe the dimension could be polynomial, and then well, the full size of the circuit would also be polynomial then. And depth polylog of the dimension. Okay. This is kind of what you get out of these so-called parallel algorithms, if you will. Okay. And so what can we do? So for example, the types of things we can do is we can compute matrix powers. I can compute m to the power k, for example. I can do matrix exponentials, so I could do e to the power m, right? And I could do things like spectral decompositions. So all of these things I can essentially do for our setting, right? Where I have matrices, m for us will be a d by d matrix, where d is very big, it's exponential. It will correspond to, for example, q, this operator we have. And in NC Poly, I can do all these types of operations, for example, right? For example, powering q, or taking a spectral decomposition. These things I can do, okay? Good. So if I take all these things together, number 3, okay, so what can I do? So I can represent my STP P, let's say. Okay, so obviously I'm fudging here a bit, but I can essentially represent the operators in P in NC Poly, right? Or again, this is also fudging because NC Poly is a decision class, but with circuits of this class, right? I can do basic matrix arithmetic, in NC Poly. Okay? You know, all's fine and well, right? What was my goal? My goal was, can I combine these to solve the STP? Right? So is there some way to solve this STP basically using just these primitive operations, things like this, like exponentiation, for example? If there is, then we're done, because we can just kind of plug in you know, these routines that are already known to do this matrix arithmetic, okay? So this is the key question now, right? And of course, the key answer is the part of the previous lecture which I've completely ignored so far, which is yes, via matrix multiplicative weights. Okay? Ta-da. Very easy. Well, okay, the result is not easy, but you know, now that we've put everything together, it's the only thing you could choose, right, in this lecture. The only tool we have left at our disposal. And so, yes, so if you do things like, you know, the ellipsoid method or other methods for solving STPs, you know, it's not clear how to do it in polynomial space, but matrix multiplicative weights will allow us to get away with this space restriction. Good. So the first thing we're going to do is we're just going to state the algorithm. Then we will just try and parse the algorithm a little bit, right? Understand it. And finally, we'll prove correctness and soundness, right? That will be the remaining lecture, or the remainder of this lecture, I should say. So let me remind you. So let me just write down these STPs again over here on the right to remind you what they look like. So first it was max the trace out of x, sorry, trace of x, I should say, subject to, I'm trying to write it a little bit smaller so I could fit everything. And so you could stare at both this and the STP, sorry, the algorithm at the same time. Okay, so this was the primal. And the dual was, again, the minimum. Sorry, other typo. Okay. Trace out of C of Y, infinity norm, subject to phi star of Y is greater than or equal to identity on C, M1, M2, and Y was positive semi-definite. And remember, Y is on just C and M1. Okay? So this was the dual D. This is the primal P. Okay? Good. So those are the STPs, and now I want to give you the algorithm, right? Which I claim will, it won't perfectly solve these, let me be clear, but it will solve them good enough. Good enough to distinguish between a yes and no case for a quantum interactive proof. Good, so let's do that. Oh yeah, sorry, let me also write down the definition of phi. Remember, phi of x was the trace out of the second message register, M2, of x, and we conjugate it with this funny thing over there. And phi star of y, the dual, was similar, not quite the same, right? The dimensions have to line up. We're going in the opposite direction now. Y tensor identity on the second message space. Okay, so these were the other definitions we'll need. Good. So maybe the best thing for me to do is let me just write down, right, the full STP, okay? And sorry, the full algorithm, and then we'll just parse it, okay? So this is algorithm 2. Algorithm 2. Oh, I don't know why that's not playing nice. Okay, algorithm 2 of the notes. And this is basically multiplicative weights for QIP. Okay. So the first thing we'll do is just we're going to make our lives a bit easier. I'm going to give names to the various dimensions involved, right? So n is going to be the dimension of the full space, meaning the dimension of C tensor M1 tensor M2. And the other one is M, and maybe I'll put these in red just to help them stand out a bit. M is going to be just the dimension of M1. okay, the first message register. Okay, now let's set a bunch of parameters. So I'm going to set, don't freak out too much about the parameters right now. I mean, try and focus on seeing the general structure of this. And that's, of course, the intuition we'll go over shortly. Right? So basically, gamma and epsilon are some constants. Delta is going to equal to epsilon over 2 times the infinity norm of Q inverse. Okay. And finally, t, the number of rounds this thing will run for. Again, maybe I should make these guys red. Right? T was, or is, 4 log capital N, right? So capital N we've defined above, right? Over epsilon cubed delta. Okay, so roughly speaking, it scales like it's polynomial, right? Notice how it's polynomial because the n is exponential, it's a dimension, but now I take a log. And then I divide essentially by constants, right? So this is polynomial in the number of qubits, t. Good. And now, let me just slowly maybe get into the intuition a little bit, right? For classical multiplicative weights, we started by saying, you know, you had, say, a bunch of professors and you wanted to get their advice for which course to take. You had no idea which professor was good and which was bad. And so what you did was you, in the beginning, you had a uniform distribution over whose advice you wanted to take, right? Because you didn't know any better. And we're going to do something similar, right? So there's going to be a notion of an initial state. Remember, we're trying to come up with a good density operator, essentially, for the prover to send, right? There's row 0, row 1. Remember, in the original protocol, there was this row 0 and row 1 that ultimately is what the verifier got once the protocol concluded, right? And so we're trying to find a good row 0, row 1, let's say, subject to the constraints of the STP. So my initial guess for row 0, for row, and the 0 here will mean that I'm at iteration 0, okay? So my initial guess for the optimal choice of row proof is basically going to be complete ignorance. And I've written W0 for a reason now. It's basically the identity to start with, but later, of course, we're going to update it, and that's why I didn't bother writing identity. I wanted it to be clear that this is the very first choice of W. Okay, and I'm actually going to need another operator, which is going to be this zeta 0. And what is that? That is, I suppose all these things should be red, technically. That's going to be Z0, which I haven't defined yet. But as you can guess, it's going to be an identity, because I don't know any better. Z0 is equal to identity, and on which space? Well, it's only going to be on space C. Okay. So the message here is that, you know, so far the algorithm is going to take a polynomial number of rounds, and my start state essentially is going to be identity, and it's normalized, of course, by the full dimension, right? Identity acts on the full space. Okay, so I have a maximum mixed state to start. That's exactly what I expect. Good. And now I have to do some sort of iterative process, right? That's what happens in multiplicative weights, right? And the only funny thing is that in multiplicative weights, the way we thought of it before was that you have a bunch of advisors, right? In each round, it's an online algorithm, right? You get some input from the environment, and then you update your distribution over the advisors, right? Whereas here, it's an STP. Like, what environment? What are you talking about, right? Where is that kind of environmental feedback supposed to come from? And so here, there's a clever trick. And what you do here, basically, is you take your starting state, let's say row 0, and essentially what you want to do is you want to see how badly it violates your STP constraints, right? I mean, so by the way, let me be clear, like this state by definition, right? Here's our STPs, right? This state by definition certainly satisfies these two constraints, right? It's certainly a density operator. Well, I normalized it, and W0 is identity, so it's positive. So it certainly satisfies these bad boys over here. The problem is this constraint, right? This one here. This is the one that's tricky. We have to make sure we satisfy this one. And so what does it mean to get kind of feedback for our current solution from the environment? Well, the natural thing to do is to say, okay, well, I can plug in my current solution, row 0, and see how badly do I violate this inequality. And dependent on that answer, I can, well, I mean, one thing I can do, for example, is I can take, I can move these all to one side, right? So I can have phi of x minus this thing. And if this thing is not satisfied properly, there'll be some residual operator, right? And then using that, you can kind of update your solution to get from row 0 to, say, row 1 to hopefully do better, to violate this a bit less next time. That's going to be the basic premise. Okay, so that's going to be the environmental input. It's you plug in your solution, how well does it do on this constraint? If it's not doing very well, you use that information to update your next state, row 1. So let me write down the actual loop now for t equals to 0 up to capital T. So what you're going to do is you're going to check constraint violation, as I just said. Okay, and again, to be clear, I'm talking about this one over here. This is what I mean by the constraint. Okay. So what we're going to do is we're going to say let pi t, because I'm at time t, right? So that's this thing here. No, let's do it right. Time t, right? Project onto a space, spanned, whoops, by, I'm trying to keep as much as possible on the screen, by the eigenvectors of what? Well, I'm going to do exactly what I said, which is, let's just move these things over to one side, essentially, right? Phi of x, sorry, what did I want to say? Let me be very careful, because in the original STP, my variable was x, but here in my algorithm, right, I'm using rho. And the reason why is because when the algorithm concludes, I'm not actually going to use the final row. I'm going to take that and fudge it just a little bit to get the proper x I want. So that's why you see different labels for variables, heads up, okay? So, but this is still corresponding to this constraint here. The other funny thing is we're going to have, where's gamma? This thing. I want to really stress here that indeed we get this identity C tensor. Well, okay, let me highlight all the variables here, right? So let's first write it down with non-negative eigenvalues. And then we want to set beta t equals to the trace of phi of rho t times pi t. Okay, so let's quickly break this down. What is this saying, right? So this is essentially trying to capture this constraint right here, right? I mean, as you can tell, it looks very similar. Again, instead of x, I have rho, and that's because when I'm done this full iterative algorithm, I'm going to then round rho to a final version of x. The other thing, oh yeah, so sorry, the other thing is that, there's this committed state sigma, and in our case, again, I don't know what sigma is ahead of time, right? So what I'll instead do is I'll make a variable out of that. That's this zeta, which we had up here, right? Remember I had these two guys and I set them both to identity? Sorry, this is wrong. This should be on M1, right? Sorry, typo. This should be M1. Okay, because that's the first message, right? And so in the beginning, I imagine I commit identity, right? And so these two I'm going to keep updating. And the other thing is that, of course, I'm going to kind of play with the amount of violation. And the way I can kind of play with that is by introducing another variable, gamma, that will dictate basically how strongly this thing has to be satisfied in some sense. Okay, so, and of course, whereas gamma, it's right here. Well, I fixed it in such a way that, I mean, if you want, of course, I could have written 4/3 here, right? That's completely fine. It's a constant, right? But the point is that when I plug in this choice of gamma, it'll turn out to do it in such a way that this constraint in the end will be sufficiently satisfied due to this kind of extra scaling by 4/3 that I can round my choice of rho properly to a good choice of x. All waving my hands here. Okay. So what do we do again? We look at this operator, right? What is this operator? This is if you brought them all to one side, and if this thing is violated, right, then I know that there are some eigenvalues of this thing, right, which have non-negative eigenvalues, right? Non-negative because I've moved it to the left side, and that's why I'm talking about non-negative on the right side, right? If I'd moved them to the right side, then I would talk about negative on the left side. So in some sense, these are kind of the bad eigenvectors, right? These are the ones that are projecting onto the wrong side of the plus minus divide. So these are projecting onto the bad eigenvectors, right? And what we're going to do is we're going to take that projector, here it is, right? And I'm going to look at the overlap of that onto this function phi of my current state rho t, okay? And that's what I'll call beta t. So I'm looking at which portion of this thing overlaps on pi t. Okay, and I'm going to use that. I'm going to use both pi t and this amount of overlap to guide, right? If this is kind of the bad space, then I can use it to guide how I update my solution, right? Because I know exactly what the bad space is. Right, it's right here. I'm staring at it, right? So now before I do that, maybe I'm lucky, and maybe my overlap with this bad space pi t is small enough that I can say, aha, I'm essentially done, right? So if beta t, if this overlap with the bad space is sufficiently small, so it's smaller than epsilon, where epsilon I defined up here, it's a constant, 1 over 64, then we just halt and accept. Oops. Okay, so turns out we don't have to satisfy the constraint perfectly. As long as we're good enough, we're close enough, then we can take the rho that we get out of this and round it to a final feasible solution x, which will give us what we want. Okay? Good. Now, if I'm unlucky, of course, and my overlap with the bad subspace was not small, bigger than epsilon, then I have to update my solution with the knowledge that I have, which is sigma, right? So update current solution. Okay? And so what we'll do is we'll set rho of t plus 1. This is the next choice of rho, right? What is it? Well, it's going to be wt plus 1, so this is the next choice of w. And this is just renormalizing now. That's kind of a no-brainer. We want it to be a density operator. And the only question is, what in the world do we set wt plus 1 to? And I'll let the suspense kind of hang in the air for a second as I just write the kind of the obvious stuff first. Okay, so remember that initially we called these two w of 0 and z of 0, and then normalized. And now I'm going to update it to the next choice of w and z. And so how do we do it? So remember that for multiplicative weights, the idea is that we always multiply to update, and we multiply by this funny exponential looking function. So you should probably expect something exponential looking to show up here, which again is fine, remember, because we can take exponentials in NC poly, right? This is exactly what we're going for, right? So let me write it down and we'll kind of stress that point. So t and delta, t is just the iteration number, right? This is the iteration. Delta, I believe, was just a constant. Where was that thing? Yeah, delta is delta is not a constant. It depends on, I suppose, the smallest singular value of q. Okay. And then what do I have? Well, then I have this lovely looking sum. If you haven't detected a hint of sarcasm, then it's about to hit you in the face, I suppose, as I write this down, which is 1 over beta j pi j. Okay, so what am I doing? All the rounds from 0 up to the current round, t, right? What I do is I sum up, basically, in each round. Remember, I had this projector onto this bad subspace, if you will. And this was essentially, I guess, renormalizing by your overlap onto that bad subspace. So I take that bad projector, and I use it, and I kind of push it through this map phi star to kind of map it to my problem, right? Because in my problem, I'm really most interested in this operator q. And remember q, which is the cost function, that's encoded in phi star, right? Remember what this is, right? Phi star is just, it conjugates you essentially by q inverse technically. And so, of course, depending on the kind of this overlap between this bad subspace and these q's when you do this conjugation, that's going to essentially drive us towards the next solution. That's the idea. Okay, and I sum over all the steps before this. So I take them all into account. Okay. And the other one will be similar. Not exactly the same, of course, but the basic premise is the same. E to the epsilon delta. Okay. And so there's no time step there. Oh, sorry. That's a typo. I was a bit surprised here. Okay, sorry. Take it back. This is independent of the time. This should just be epsilon delta, just like this. Okay, so these two should match, right? So the only place the time shows up is the one place I haven't written it, in fact, which is this one, right? There's the time. And so here I have e to the epsilon delta, the sum, over j equals 0 up to t, same as before, okay? And now, instead of having this thing, I'm going to do something slightly different. Remember, this is my guess for the committed state, okay? And so this is going to look different, of course. It's going to be 1 over beta j pi j. Okay? So these are the operators that turn out to work. Okay. And that's it. And the last step is just to reject, step 5. So if you finish this loop, where's the loop? Maybe I'll zoom out just a touch to see if I can get it all on screen at once, or maybe a bit more of it, okay? Here's the loop, right, step 4, right? If you finish this loop and you haven't ever accepted on step, 4b, right? Meaning you never got to a point where you satisfactorily satisfied that one inequality constraint we care about, then ultimately we exit the loop and we just reject, okay? That's the basic premise. Why does this algorithm run in p-space? Well, equivalently, why does it run in NC poly? Well, we said I can write down these operators, for example, all in NC poly, right? There are circuits to prepare those, right? And certainly I can prepare Q, right? And that means that I can do these things, right? If I can prepare Q, then I can do things like exponentiation according to Q in NC poly, right? Because, this is e to the, phi star here, for example, right? So I can certainly compute this matrix in NC poly, and then I can do the exponentiation in NC poly. So in other words, I'm claiming, I haven't proved it, that when this thing concludes, right, the values of rho and zeta I get out, I can round them nicely to proper x and sigma for the original STP, so that they'll be close enough to the true answer to the QIP STP. That's it. And then we'll be able to decide whether it was a yes instance or a no instance. Okay, so pause for a second, make sure you understand that important lesson, which is this is why we get containment in p-space, right? This, I'm claiming, is going to give us a way to solve the STP by doing basic matrix operations like exponentiation, sums, right? No funny ellipsoid method, no interior point methods, nothing funny like this, okay? And that's why we can do it all in NC poly. Okay. Now, let me really stress, I've said this a few times, but let me really stress it again. Algorithm 1, this is algorithm 2, does not output a solution x comma sigma to the primal STPP. It doesn't do that, okay? Instead, what it does is it outputs, remember, some rho and some zeta, essentially, right? And the idea is that, here's the idea. We're going to prove it, of course. If we're in a yes case for this QIP protocol, let's say, for the QIP instance, right? Then we can basically round or extract rho zeta to some good solution, sigma, to the primal STPP, okay? And this will be a good solution, and I'll explain what that means shortly, right? And if we're in the no case, likewise, we can do a rounding. What am I going to do? We can round the dual solution, right, which is y. Sorry. Where is my dual solution? Okay, so we're not going to round, we're going to be a little bit more careful. We're going to actually round the beta t's we encountered along the way and the pi t's, right? And we're going to round those to a dual solution y, to the dual STP. And this will be bad, right? It'll show us that the value of the STP basically is sufficiently small. Okay, and again, I'll tell you what good and bad are in a second. Okay, so now we're ready to show correctness. Okay, so that means, of course, we want to show completeness and soundness. Okay. And so let's just set up the basic framework, right? So this is 3.2, correctness. Okay, so we have some QIP promise problem, right? A yes, A no, A invalid, B in QIP. Okay. And of course, we're assuming this thing has a 3-round quantum interactive proof. Okay. And what we're going to assume is that this thing has completeness in the S case, right? There'll be a protocol that's accepted with probability exactly 1. And in the no case, we'll pick the specific bound of a half plus 1 over 64. I mean, this just works. I don't really think there's anything particularly special about it. Remember, we can pick any value strictly above a half. Okay, so these will be the parameters we'll assume for the QIP protocol. Okay. Okay, so what this of course means that is that if the input x, right, is in a yes, right, that implies that p has opt value. Or maybe I should write it this way. The optimum value for p, right, equals to 1, right? And if x is an a no, then the optimum value of p will be at most a half plus 1 over 64. Okay, so this is what we get out of it when we just pass that through to the STP. Good. So what is the main theorem we're going to show about the algorithm, algorithm 2? So it's theorem 35. And it says, if algorithm 2 accepts, then the primal feasible program P, or maybe I should say like this, opt of P, right? Okay, let's do this properly. Opt of P, right, will be strictly larger than 5 over 8. If, on the other hand, the algorithm rejects, then opt of P will be strictly smaller than 7 over 8. Okay. Exercise 36. Immediately, you should ask yourself, why does this work? Right? I mean, the lower bound is smaller than the upper bound. What? Right? Why does this work? Normally, I mean, we always said in the S case, you accept probably say 2/3, in the no case, probably at most a third, right? They were always in the right order, if you will. So why does this allow us to decide between these two cases here, right? And, well, the answer is pretty straightforward. I'd encourage you to pause the video and think about it. You don't really need to prove anything. But basically, the only way you can get 5 over 8, right, is if you're in the S case. Like if the real solution was 1, and we can get, then it's possible for us to get 5 over 8, right? But if the real solution was a half plus 1 over 64, that's strictly smaller than 5 over 8. You know, there's no way you're going to yank out a solution now that will give you at least 5 over 8 in this algorithm, right? Because ultimately the algorithm will only give you something that's upper bounded by the true optimal value, right? And in the no case, if I get a value at most 7 over 8, right, then I know that certainly I'm not in the yes case, basically, right? Because in the yes case, I know, like, so, okay, sorry, let me be clear. Yeah, so let's be clear. We're not talking about, I'm giving you a solution, right? I'm really saying, let me just verify this. Right, I'm really talking about the optimal value. Okay, so I think that I had a slight moment of confusion there, right? You're really talking about the optimum value, right? You're not saying, it's not just some feasible solution. I'm not saying there exists a feasible solution with these values. I'm saying the optimal value for the STP is at least this, which can only happen if the true value is 1, or it's at most this, which certainly would contradict the fact that the optimum value is really 1. So you must be in the no case. Good. Maybe I should have paused the video and thought about it, right? Good. So we're going to break this down, of course, into 2 lemmas, one for the S case, one for the no case. Right, so this is proof of theorem 35. Lemma 37. Yes case. Okay, so this is when x is in AS. That's this case up here, right? And now we know the optimal is 1. And so what we want to prove is basically this first line over here, right? So I'm not going to rewrite it. Basically, if algorithm 2 accepts, then I claim to you that the optimal solution is at least 5/8. Okay, so what are we going to do? Well, to prove that the optimal solution is at least something, right, I can give you some feasible solution, which gets value at least 5/8. And that will tell you that, the best solution, therefore, has to be at least as good as the possibly not so good one that I gave you, right? So that's what we're going to do. Okay, so to prove this, recall that, here's the proof. First, let's think about what the algorithm outputs, right? So algorithm 2 outputs 4 things that we care about. I'm going to give them names, row, I think that we call that zeta, pi, and beta. And which ones are these? Well, these are, remember, these were all indexed by t before for the time step. But so this is going to be the final value, would be the final values to, row t, zeta t, pi t, beta t, right? So in the last iteration of the loop, when something good happened, we accepted, we saw that the error was small, remember, and we exited the loop prematurely, right? So what do we do? I'm going to take these output values in particular and just round them. So here's the claim to an STP solution, right? So remember, for the STP solution, I need to tell you x, right? Which is the final joint message, and the initial committed message, which was sigma. Okay, so x is what? It's going to be basically rho. So it's the same thing here, actually. We don't really change this, other than I'm going to rescale it. Okay. And the other thing I need to tell you is sigma, which was that first half of the committed message, or well, the committed message. And what is this? This one's a bit nastier. Again, I'm going to do this renormalization, same factor actually. What's going to change is what comes inside. And now it's going to be a mixture of both of these states. Okay, so on the one hand, I'm going to have, again, this gamma, and then times the zeta operator. So let's be clear, this is a matrix. And the other part of the mixture will be 2 times the trace of the, the check qubit pi phi of rho pi. Okay, so these are 2 operators I can construct. And the claim is that these together are a feasible solution to P with value at least 5/8. Okay, that's the claim. So this is what I was talking about earlier, that we're going to take the outputs of the algorithm and we're going to round them to some final solution to the STP x and sigma. Okay. So, well, what do we need to verify here, right? So I have to verify 2 things, right? So number 1, that this is a feasible solution to the primal STP, and second, that it has a good optimal value, right? So exercise 38 says that, well, let's go back to the objective function, right? Remember, the objective function was, okay, any day now, there it is, right? The objective function was just trace of x, right, under our renaming of the variables, or changing of the variables. So it's just trace of x. So remember, my claim is that the trace of x should be at least 5/8, right? So show that the trace of x is strictly larger than 5/8. Okay. And I mean, you could sort of stare at this. I mean, this is the exercise, but I mean, what are you doing? You're taking the trace of this thing, right? So what is the trace of this thing? Remember that, by the way, x does not have to be normalized in the STP, right? We're using that here. Sigma had to be normalized, but not x. And so rho over here, by construction in algorithm 2, it was always a normalized operator. We always took the effort to renormalize it. And so really, you're just interested in what does gamma plus 2 beta equal to. And well, if we go back, let me see if I could track down gamma and beta. Gamma was 4/3, and beta was, it was this, the size of the deviation, right? Which is going to be small at most epsilon, right? So roughly speaking, this is going to scale something like 3/4, roughly, right? Up to some small fudging by the beta factor. And so the trace of this will be, roughly 3/4, which will be bigger than 5/8, of course, right? So that's essentially how you get that exercise. And then the other exercise, of course, the other sanity check you should do is show that sigma is a density operator. Okay, so take the trace, for example, and make sure the trace is 1, right? And I mean, you can sort of see there's gamma already here and a gamma here. And you also have to prove it's positive, right? And how do you prove it's positive? Well, it's a sum of 2 operators, right? This one is positive by construction, right? It was a density operator. And this one, well, it was positive, and then we pushed it through this map, which was a conjugation, and then we conjugated by pi, and we took a partial trace. All these preserve positivity. So, and the sum of 2 positive operators is positive. Intuitively, that's how you should go about proving that. So the main thing to do is the one constraint we have to satisfy that's non-trivial in the STP, which is remains to show that phi of x, right, less than or equal to identity C tensor sigma m1 is satisfied. Right? This is that one. Go back up. It was that one constraint in the STP, right, this one in red, that is non-trivial, right? So let's verify that indeed we satisfy this constraint. Okay, good. So this is just going to be one chain of equalities, right? This is actually going to be fairly simple. The S case is the easier one of the 2 to prove. Okay, so what do we do? So let's just kind of rearrange phi of x minus zeta of identity C tensor gamma. Gamma, and this is zeta. Right, so this was going to be what we got. So remember in our STP, like this was the quantity we were concerned with, right? Because we defined pi. Let me be a little bit careful here. Where's my pi? Ah, okay, right. So we looked at this thing, right? Phi of my solution basically minus gamma times identity tensor zeta, right? And then pi was supposed to be the projector onto the non-negative eigenvectors of this, if you will, right? The eigenvectors with non-negative eigenvalue. Okay, so that's why you see the similar expression showing up here, right over here. Okay, so what is this thing? So this thing, first of all, I claim is going to be at most pi times phi of x minus gamma identity of C tensor zeta. Okay, so the only thing that's changed here, by the way, is pi. Okay, so why is this true? Well, we just look at the definition of pi, right? Pi was supposed to be the projector onto the non-negative eigenvalue space, basically, of, well, precisely this operator, right? What's here in the middle. So essentially this one, all the negative eigenvalues, it throws them out, basically, all the eigenspaces corresponding to those, and just keeps the non-negative part. And so certainly this thing will be bigger than this thing in the PSD ordering. Okay? Because we just threw out all the negative stuff, right? Okay? And then the next thing we do is, then I claim that this thing will be at most pi phi of x pi. Okay, and this one's a little bit easier to see, just simply because all I've done is I've thrown out the second part, right? This identity tensor zeta. And why can I do that? Well, this is simply because, if this thing here, right? This is certainly going to be smaller than just phi of x, right? I mean, because both this is positive, I mean, I'm ignoring the minus sign, right? I mean, separately they're positive. So if I take the difference of two positive operators, think in terms of numbers if you like, then certainly that's always going to be at most, the first positive number I started with, right? So same thing with real numbers. So that's how you get that one. And finally, we have one more. And this will use a non-trivial fact, which we won't prove here. But basically, I'll write down the fact in a second, but this is what you get from the fact first. Trace out of C of pi phi of x pi. Okay. And so here we're using this fact that since MAB, for some matrix MAB, is at most 2 times A by A times the trace of M. Okay, so in other words, if I had some bipartite operator M, if I trace out the first part of it and instead stick in an identity, then that will always be bigger than the original operator if I put in a prefactor of 2. Okay? And so the one place where you really see this happening is that if M, say, is a projector onto the Bell state on 2 qubits, right, you will precisely need to put in this prefactor of 2 to get equality here, basically, right? You can't get away with anything less in the worst case. Okay. Okay, and this completes the proof of, oh, sorry, this is, let me be clear, this is for any MAB greater than or equal to 0, A is equal to just this, complex. Okay, so I have this chain of equalities now, right? And so, of course, the main ones I care about are I have this on the left, right? I have this on the right now. And so now I just rearrange, right? What I wanted to say was that phi of x, I wanted to satisfy this one up here, right? So, but now if I just move, this part over to the right-hand side and rearrange, you'll see that I'll get exactly what I want, because I'll get phi of x on the left and I'll get identity tensor sigma 1, where sigma 1, remember, was defined as this mixture of zeta and this funny projection here, right? Or this projection of phi of x. And that's exactly what you see here, right? Here's your zeta part, and here's your projected term involving phi of x. Okay, so that's it for the proof of completeness. Okay, that's slightly easier. And let's look at the no case. So this is going to be lemma 40, no case. And here, remember what we wanted to show was that if, so okay, by the way, in the yes case, it was, remember, easier to do the proof. Why? Because to prove that the optimal value is at least some value, say 5/8, I don't have to actually tell you what the optimal is, right? I just can pick some good enough solution, and that will be a lower bound on the best solution, the lower bound on the true optimal value. In the known case, it's a bit different, right? I need to basically upper bound the best solution, right? But of course, how are we going to do this? Well, we have SDPs, we have a primal and a dual, right? So the beauty of SDPs is that now I can do this, right? I can upper bound the optimal primal solution by instead looking at the dual, and I don't have to solve the dual perfectly. I can solve the dual good enough, right? And remember, by duality theory, and in particular in this case we have strong duality, a good enough solution for the dual will give us a good enough upper bound on the primal, right? That's the premise here. So in the no case, if algorithm 2 rejects, P, sorry, I was using this other notation, opt of P is going to be strictly smaller than 7/8. That's the claim. Okay, so again, how do we do this? Strong duality, right? I'm going to give you a good enough solution to the dual that will show you that the dual value will be strictly smaller than 7/8. Okay, so therefore, so is the primal value. So claim a dual feasible solution is y equals to 1 plus 2 epsilon. And here we have to be a little bit more careful. We're actually going to use those projectors pi t in each step, right? So I'm actually going to use all of them here, right? So you'll notice that I have a sum over all time steps now, little t, sorry, t minus 1, 1 over beta little t, and then there's going to be a t here. Let me write it first, pi t, okay? That's what I claim is going to be the dual feasible solution. And the objective function value of this is going to be, so the objective function value. And remember the objective function was this funny thing, trace of y, trace out of c of the operator y. That was the infinity norm, right? That was the objective function. And the claim is that that will be larger than 7 over 8, right? Exactly what we see up here. Okay, so again, just like this is the beauty of working with STPs, right? You just guess a good enough solution, right? And then you have to prove that that solution is feasible and gives you the bound you want. Okay, you don't actually have to solve the STP perfectly. Okay, so the proofs of, there are two things I have to show here, right? I have to show, right, that this solution is first feasible, it satisfies the constraints of the dual, and I need to show that the objective function value is at most 7 over 8. Now both of these proofs of these statements are quite similar, so we're actually only going to show the first of these in class, right, for brevity. So let's just focus on showing that y, as stated, is actually dual feasible. Okay. So let's quickly have a look at our dual again, right? Maybe I could even copy it and bring it down for a second. Or it's probably even faster just to write it from scratch at this rate. There it is. All right. Okay, let's see if I can copy this thing. Oop, that did not work. Oh, I have to do it with my pen, sorry. All right. Is it working? Nope. All right, let's just rewrite it. Maybe that's just the easiest way to do this. Ah, okay, it's stalled for a second. All right, are we going in? Oh, wait, no, it worked. No, it didn't. Okay, whatever. I'll just rewrite it. Okay, so what was the dual? This was, you want to minimize TRC of y, infinity norm subject to the constraints that phi star of y is at least identity and y is positive semidefinite. Okay, that was the claim, and remember that phi star of y is just equal to y tensor identity q inverse. Okay, so let me just rewrite that there. Okay, and now of course the claim is that this operator is dual feasible. So what is there to check? Well, there are these two conditions to check, right? So first, y being positive semidefinite, that's obvious, right? Because pi is you're just summing up projectors. They're all positive by definitions, and the sum of positive operators is positive. And of course, these weights are all positive too, obviously, right? So, this one is easy. We get that right away. This is the one that we have to really kind of think about a bit, okay? We need to argue that when I push this through the map phi star, right, I'll get something that has minimum eigenvalue at least 1. Okay, that's what I need to show. Okay, by the way, exercise 41 is what gets you to check this. Okay. So how do we prove this, the red one over here, right? We're going to use an approach actually that's similar or inspired by the classical multiplicative weights analysis. And there, remember, the idea was that we picked a potential function to focus on. In that case, it was just the sum of the weights over all the time steps. And then we gave upper and lower bounds on that potential function, and then we threw away the potential function, and we just stitched those upper and lower bounds together and rearranged to get what we wanted. And we're going to do exactly the same thing. Use a potential function, quote unquote. And in our case, the potential function will be very similar, right? It will be, instead of summing the weights over all time steps, now what I'm going to do is I'm going to take a trace over the teeth kind of weight operator, if you will. Okay, WT. That's going to be the potential function now. And again, we're going to show upper and lower bounds on trace of WT. And then we're going to rearrange to get this identity over here, right? That phi star of y is at least identity. Okay. And so, just for clarity, I've already said this, but, exercise 41 gets you to show that that y is indeed positive, right? So that, this constraint really is satisfied. So if you didn't follow the argument, feel free to pause and think about that. As for the lower bound on the trace of WT, right? So again, I want an upper bound and a lower bound on the trace of WT, and I'm going to stitch those together, and then I'll get the final bound I want on phi star of y. Okay, so let's start with the lower bound. Maybe I'll put this in blue. Theory, it should have been blue. Taking a moment to switch. Okay, so the lower bound is fairly simple. And how does it go? Well, okay, well, let's decide not to be blue, and that's fine. We're going to use the same principle as the classical lower bound. In the classical MW method, right? And there, to give a lower bound on our potential function, we use this very simple idea that if I have a sum of non-negative numbers, that's always at least as big as the smallest number. At least as big as the biggest. Well, I guess we use something weaker. It's always it's always at least as big as the smallest number, or any number, of course, in the sum. Okay, so sum of where these are non-negative is, of course, greater than or equal to all of them. And in particular, of course, it's bigger than the smallest one in the sum, right? If they're all non-negative. And we're going to do something very similar here, actually. Okay? Because, intuitively you have a trace, right? What is this doing? It's summing up eigenvalues. So in particular, that means that you could lower bound this by just looking at the smallest eigenvalue, right? They're all non-negative. It's a positive operator. Okay, so, and this is exercise 42 now. So what it wants you to do is, look at this potential function, trace of WT. Let me first write out what it equals to, right? This is the trace of what? It's e to the minus, and this is just what algorithm 2 tells us, right? And I don't know why I switched to a j here. Okay, so t minus 1 of phi star of 1 over beta j pi j. Right, so this is just what we would have gotten as the last value of WT, right, when the algorithm exited the loop prematurely. And now the claim is that this thing is at least as big as, let me move this around for a second, e to the minus epsilon delta, right, so that hasn't changed, right? Whoops. Took a moment to kick in. Sorry, let me just erase this then. E to the minus epsilon delta, right? And now something has changed, right? On the left-hand side, right, what you see here is an operator, right? And then I took a trace, right? So in other words, it was the sum of the eigenvalues of this operator. And now I'm just going to put down a scale. There are going to be no operators involved. So e to the lambda min, the smallest eigenvalue, right, of what? Of the operator I had before, but I have a lambda min in front, so now it's going to squish that down into a scalar. Sum over j equals 0 up to t minus 1 of 1 over beta j t pi j. Okay? This is the claim. So again, take a moment to pause and think about this. What's the intuition? Why is this true? Well, the trace on the left is the sum over all the eigenvalues of what's in this bracket here, right? What are all the eigenvalues of that thing? Well, you take, remember, what it does is it takes the eigenvalues of what's in the exponent, this operator, and then it just hits them all with an exponentiation, right? And then it adds those up. That's what the trace does, okay? So instead of adding up all those e to the minus whatever terms, right, just pick the smallest one of those and keep that one. That will give you the lower bound, right? That's exactly what we set up here. And that's exactly what this is doing, right? it basically picks the eigenvalue out of that operator, which is going to result in the smallest exponentiated value. Okay? Oh, sorry. I suppose we're using the biggest one. Sorry. I think this is a, yeah. Yeah, I think this is certainly true what I wrote up here. But here in particular, of course, it'll also be bigger, because here we choose the minimum eigenvalue so that, you know, this exponentiation is as big as possible, right? Because we want a good lower bound, right? So if I pick the smallest eigenvalue here, then it's going to push you the least, you know, the inverse exponential function should go like this, right? So it's going to keep you somewhere higher up, right? You're going to try and keep stay as much to the left as possible, right? So so we're going to pick the smallest eigenvalue, which corresponds to maximizing the right-hand side. Again, we want the best lower bound possible. Okay, good. So that's where this comes from, right? This claim. Again, that's an exercise. I mean, I've more or less sketched the proof, but again, I leave it to you to really sit down and think about it. So that gives us a lower bound on this expression here, right? Whoops. But we didn't want just the lower bound, we also wanted an upper bound, right? So let's do that. Upper bound on the trace of WT. Okay, this is just like classical MW analysis, okay? Okay, so what do we want to do? So here's kind of the goal, right? I want to upper bound, obviously trace of WT. What was that? So let me just remind you. E to the minus epsilon delta. This is just the definition again. Okay, this is what I want to do, right? And so what do we want to do? We want to do this inductively, right? I mean, notice how I have this sum over here, right? I have a sum over all the time steps. That's really annoying, right? What I would really like to do is take, you know, this full thing over all the time steps and kind of strip out the last time step and then kind of recurse inductively, right? That's kind of our goal. And, you know, normally, if this wasn't an operator, right? This is an operator, but if it was really a scalar, there's no problem, right? Because if I have a sum here, that would correspond to, you know, these are exponentiated. They're in the exponent, right? So a sum in the exponent corresponds to a product in the base, right? I could just literally strip off that last time step. But because they're operators, I can't do this, right? In general. Okay, so remember that if you have a sum of operators in the exponent, then you can only break them into a product if those operators commute, right? If all these terms in the sum pairwise commuted, right? But in general, that's not going to be the case. Okay, so cannot convert sum into, sum in the exponent to a product in the base since, you know, these guys over here, these phi star of 1 over beta j pi j, this set of operators don't commute, right? Or okay, at least we can't assume they commute, right? Maybe in some cases they will, but in general, we have no reason to believe they commute, right? And so it would seem we're in a little bit of a problem. We have a bit of a problem, right? Because we want an upper bound on this thing, right? And I want to do it inductively. Well, luckily, it turns out that if I don't really care about the full operator, but I just want an upper bound on the trace of the operator, we can still play this trick of going from sum in the exponent to product in the base. And there's a fancy inequality we apply. And solution, use the golden Thompson inequality. And what does it say? It says that if I have the trace of e to the a plus b, right, I have a sum in the exponent, then I could break it up into the trace of the product. Okay? And of course, this is for Hermitian A and B. Okay? So if all I care about is the trace, right? Certainly, you know, these two operators will not be the same in general, right? But if all I care about is the trace, then that's kind of like it's taken these operators and squished them into this one-dimensional space. We've thrown out enough information that indeed I can give some sort of like relationship between these two. Okay? And this is all I care about, right? Because I just want an upper bound on trace WT. I don't care to know exactly what you know, WT is per se, for example, right? I just want an upper bound, and I want to do it by stripping off in the sum. I want to strip out the very last term where j is equal to t minus 1. Okay, that's what I want to do. Boom, right? So the next exercise says the following, right? So basically the remaining exercises are just guiding you through this. What does this say? It says that for any t, oh, we need some braces here. Okay, for any t from 1 dot 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 up to capital T. So use this golden Thompson inequality to show what that if I take the trace of WT, right, then that is what? So here's this is what I had, right? So trace of WT is just this crazy thing over here. I want to do this in an inductive sense, right? So what does that mean? I want to write it as the trace of WT minus 1 now, right? So, you know, we're stripping off the last time step times something I'm removing now for the last time step, and that's going to be e to the minus epsilon delta phi star pi of t minus 1 over beta of t minus 1. Okay? So this is the claim. Okay, and this more or less follows immediately from the golden Thompson inequality, and I'll let you kind of sit down and think it through. Okay? So, but you know, intuitively, this is just the last term in the sum, right? That's all it is. It's the case when j equals to t minus 1. Sorry, this should be t minus 1. Yep. Oh, sorry, this is for any t. Sorry. This was for any time step t, not just the very last one. Okay, because we're going to use this over and over again. Okay, good. Okay. So that's the first kind of hint of how we're going to start this induction, right? And so now we've kind of isolated this last term in the exponential, right? We've just removed the last one. And now what I want to do is, I don't like exponents, right? I mean, this e to the something, you know, that's bothering me. Ideally, what I want to do is I want to bring the exponent down into the base, right? And so for this, you know, it's good enough to use some inequalities. And so let me just state those. So now we want to bring this down, we want to use the fact that for any, Hermitian M, which is between 0 and identity, okay, and for all positive real numbers, two inequalities hold. E to the Rm is at most, this is an operator, so in the positive semidefinite ordering, R e to the Rm. Okay, so in other words, I can bring that Rm out of the exponent into the base if I write the right side this way. And so I added, you know, a multiple of the identity, for example. And the other one we have is e to the minus Rm is at most identity minus R e to the minus Rm. Okay? So we're going to use this fact, and you know, by taking this thing, right, and I suppose we want this one, right, and combining them, we immediately get that e to the minus epsilon delta phi star pi t minus 1 over beta t minus 1 is less than or equal to identity minus epsilon delta e to the minus epsilon phi star pi t minus 1 over beta t minus 1. Okay, so that's what we literally get. And here, you know, I believe I'm treating here I'm treating m, like you have to be a bit careful. There's a reason why I wrote this bracket this way, right? I separated the epsilon by itself and I put the delta in here because I'm treating this as the m that you see over here, right? I'm treating that together. So that's why over here, the reason why I'm saying this is because you're seeing the exponent, you only see the epsilon here. You don't see the delta. Okay, so what this means is that I can take this thing, I wanted to upper bound this, right, for arbitrary t inductively. I could always write it as a t minus 1 term times basically, instead of this funny exponential, I can just plug in this thing now. Okay, so everything now is kind of on the ground floor, if you will. Good. So let me just state some exercises here, right? So exercise 44. This says that prove basically that the norm of what I called m, so m, and m is over here, this operator, right? This is at most 1. Okay, I won't go through that here. Okay, so now that what exercise 44 tells us, right, is that now that we know that there's this norm bound on m, which is the requirement to use this one, right, because we need m to be at most identity, now we can go ahead and use this star. Okay, we know this is valid, this holds. And so I can plug in this star into this top inequality up here, which is what we wanted, which is what we got via Golden Thompson. So let's do that now. Okay, and this is exercise 45 in the notes, but I'm going to slightly expand on it a little bit more. Okay, so first let's just write this out, right? This is what? This is going to be the trace of WT, right? And what does that equal to? Well, I know now it's at most the trace of WT minus 1, so that's just what we had up here. And now I'm going to plug this in, of course, and I'm going to get identity minus epsilon delta e to the minus epsilon phi star pi of t minus 1 over beta of t minus 1. Okay, this is what we get. And so now what do we do? Well, now, of course, you could just do the trivial thing, which is just expand this out. So I'll get one copy of WT minus 1 there, right? And then I'll get the trace of, okay, let me just pull out the constants here first. I'll get the trace of WT minus 1 times phi of pi t minus 1 over beta t minus 1. Okay, that's what we'll get. And now what we have to remember here is that the definition, let me just make sure I get this right, right? Remember here that the definition of rho t minus 1 in particular was equal to WT minus 1 over the trace of WT minus 1, right? So why am I doing this? You know, I would love to have two copies of WT minus 1 kind of sitting in front here to factor out, right? But right now the WT minus 1 is sitting inside this inner product, right? I can't quite do that. So, but what I can do is I could rewrite this in terms of rho of t minus 1, and then I'll get this extra copy of the trace hanging around. So what I'll get then is I'll get this thing, minus epsilon delta e to the minus epsilon, times the trace of WT minus 1. Sorry, maybe I'll write it on the next line so that it fits properly. So minus epsilon delta e to the minus epsilon, the trace of rho t minus 1 now, yes, towards the end of the lecture, and certainly towards the end of the year, the whiteboard decides to be quite unresponsive. Oh, there it goes. All right. So what do? I'm going to have ultimately trace of WT minus 1 times phi of pi t minus 1 all over beta t minus 1. Okay, there it is. And of course, now I could bring out the normalization factor as trace of WT minus 1. Okay, so that's just plugging in this equality we had up here, right? And now life is essentially good because, you know, I have two copies of WT minus 1 sitting around here and here. I can just factor that out. So I'll get the trace of WT minus 1, right, times 1 minus epsilon delta e to the minus epsilon the trace of rho t minus 1 times phi of pi t minus 1. Okay? Okay, and does this look about right? And of course, what we can do here is, this is a scalar, this beta, right? This is just a scalar. And if you look at the map phi, what it does, right? It takes its argument and it just kind of conjugates it with an operator, Q inverse in particular, right? The square root of Q inverse. And so this scalar can essentially be pulled right out, right? It's not going to be, the map phi won't really do anything to the scalar, right? So instead, what I could write it as is essentially all the same thing, right? But the trace of wt minus 1 times 1 minus epsilon delta e to the minus epsilon. And now here, on the denominator, I could just put bt minus 1, right? And on the numerator now, I could have the trace of, sorry, this should be a star, right? Sorry, this is important, right? So there we had the adjoint. Sorry, this should be the adjoint. I made a mistake. See, over here it was right, and then I stopped carrying it around, right? It's important, and remember, the adjoint is the unique linear map, right? That in an inner product like this, like rho times the adjoint of this, that's completely equivalent if I instead of phi adjoint on the right, I can just apply phi on the left. And that's exactly what this is going to do now. It's going to take phi, and it's going to apply it to the rho term instead, right? This is just by definition of the adjoint, pi t minus 1. Okay, and the other thing is, so this is by definition of the adjoint map. Okay, and beta was just a scalar, so we took it out. Okay, so this is the final expression we get in terms of this bound. Okay, and we're essentially done, right? So remember, we want an upper bound on this trace, on this potential function. Here it is, right? We get this thing. And now, now we want to recall what was beta now, right? I have this beta sitting around. Well, remember that by definition, beta t minus 1 was precisely equal to the trace of phi of rho t minus 1, you know, times pi t minus 1. Okay. So that's literally exactly what you see here in the numerator, right? And remember that for all real r, 1 plus r is at most e to the r. So what do we get? We conclude, therefore, that the trace of wt, this is what we've been trying to bound this whole time, right? In terms of the second part of this potential function analysis, right? Trace of wt, we're trying to get this upper bound. We got all the way here. We know that these two will essentially cancel out. This will go to 1. And then I have this 1 minus this funky thing. And so then I presumably will use this identity now. And what we should get now is just the final upper bound, trace of wt minus 1 times e to the minus epsilon delta e to the minus epsilon. Okay. That's how we get this final step. Okay. So this gives me the upper bound on the potential function. And remember, I also had a lower bound that we did previously. And so now, of course, we combine them. And I will let you do that on your own. But basically, the idea here is that combining upper and lower bounds, we have the following, that the smallest eigenvalue of phi star, and remember the goal is that I wanted to show that the smallest eigenvalue of this operator was at least 1, right? It was larger than the identity. Okay. Phi star of the sum of j equals 0 up to t minus 1 of 1 over beta j, pi j, is at least t e to the minus epsilon minus log n over epsilon delta. Okay, so I'll let you kind of plug those upper and lower bounds together, but that's essentially what you should get. And of course, remember, our goal is to show that this thing is strictly larger than 1. So now I have this funny lower bound, right? But intuitively, this should be bigger than 1, right? Now, why? I mean, so capital T is polynomial, right? It's the number of steps. It's the depth of the circuit. So it's the number of steps of the, it's not the number of steps of the verifier, but it's the number of times, sorry. T was the number of loop iterations we did in our algorithm, right? In algorithm 2, but it was defined as logarithmic in the dimension. So it's polynomial in the number of qubits, right? So here you have some polynomial in the number of qubits. You know, this is also roughly polynomial in the number of qubits, and then you have some scaling factors. So if you look at the exact values of all these parameters, you'll see the following, which is exercise 47. Okay, and that states that recalling the definition of y, 1 plus 2 epsilon over t times the sum over t equals 0 up to t minus 1, 1 over phi, so 1 over beta t pi t. So now you have to use the fact that e to the minus epsilon minus e squared, sorry, this should be an epsilon here, minus epsilon squared over 4 is strictly smaller than 1 minus epsilon, to show the last thing we want, which is lambda min of phi star of y is at least 1. Okay. So over here in particular, right, what do we have, right? I have this thing here, phi star of this thing, which is just this part, right, of y. It's not the full thing. I'm missing these scalars, right? So this gives me a lower bound on this thing without this rescaling. And of course, then you have to, once you have this though, then you can multiply left and right by these scalars basically, right? Because the eigenvalues will just scale accordingly. And then when you put it all together, you should get this bound. Okay, this is the idea. Good. So that's actually it for, do I want to make sure I say anything else? Let's see. So let's just very quickly recap, right? What was our, where's the algorithm? All right, so we had this algorithm, algorithm 2, here it was, right? And what it did is basically it started at the beginning by starting with row 0 and zeta 0 as being guesses for the initial joint state and the initial committed state in the first message round. They were just identity to begin with because just like in usual multiplicative weights, we don't know any better in the beginning. And then in each round, we just checked how much we violated this one constraint of the primal STP, okay? And used that violation, right, to guide how we updated our next choice of operator, our next guess, right? And that was essentially down here. This thing decides to scroll up in a second from now. Okay, but basically, the updates were done in a multiplicative fashion, right? Just like before, like there was an e to the I term, e to the something term, basically, that we multiplied by. And finally, to do the analysis, basically what we showed is that in the yes case, if we started with a yes case of this QIP protocol, then basically I could take the output of this algorithm 2, and I can round it to some choice of STP solution that was good enough. That would give me some value that was strictly larger than, I think we said, 5 over 8, right? Which would be enough for me to conclude that I must have been in a yes case to begin with, right? Because then the optimal is also at least 5 over 8. And in the no case, what we did is that we need to upper bound. We need to show the optimal value of this STP is not too big. It's, in particular, we want to show it's strictly smaller than 1, because that's enough to conclude we're in the no case. And we did this by constructing a dual feasible solution. And to analyze that was a bit trickier. We had to, in particular, use this golden Thompson inequality to kind of inductively strip off the last term in this exponential with a sum at the top. Okay? Good. And so that was how we essentially solved this QIP protocol, or decided whether the answer was 1 or 0 in NC poly, right? We only had to do these basic matrix operations like exponentiation and spectral decomposition and things like this, and this can all be done in NC poly. Okay, so that's not it for the course, of course, but it's it for the year 2020. Okay, so oh, now it's scrolling. Okay, so that's it for the year 2020. There will be no more lectures until January. So I wish you all a good holiday, And as always, please stay safe. Follow all the COVID guidelines, and we will see you in a couple of weeks. All right, so have a good one, guys.